back in the 80s when I was in grad school, there was this notion of peace through strength. And so this is actually the reverse of that, security through weakness. And let's see, somehow, when I click, it should, next, there we are. How's that? Okay, great. So here's the outline. Briefly, I'm going to be talking about why basically is there malware? Why do we have security vulnerabilities? And the answer is going to be, well, it's bugs. And that's going to be basically all I'm going to say about security. It's all about bugs. And then the rest of the talk is how do you find bugs? And in particular, why you might care about having relatively weaker rather than stronger models of computation. And a couple of case studies, one from the early 90s that was a sort of cautionary tale, and one, or from the 90s that was a cautionary tale, and one that has been much more, that has been very recent and accidental, which has been much happier, software-defined networking. So and along with that. So if you take a look and say, where does malware come from? Right? You go and you take a look and say, well, these are bugs, by the way, and on a better screen you can see them. They're actually very pretty. You know, when you look at these slides are online, so you can find them. So in general, malware exploits a bug. It isn't always true. Some people mention phishing attacks so that you can delude users. But as a broad stroke, if you got rid of bugs, you would have many fewer security problems. So there's our message. Prevent bugs, stay safe. And so then the question is, and that's the last thing I'm going to say about security, all the rest of it is going to be about bugs. So now, hey, look, just write code without bugs. What is the matter with you people? And by the way, it came up earlier. Somebody said, well, you know, people try and write this out. Yeah, people try and write bug-free code, right? I don't. I try, but I can't. I can't generally do it. And the reason that we have trouble is, well, it's all this guy's fault. There was a movie about him recently. And of course, we all know, we've talked earlier in the day about the Turing incompleteness theorem, right? You cannot determine if a Turing machine halts, which is to say, given a Turing machine, you can't find out if it has a bug. And not only can you not, in theory, find out, right, that in the sense that almost all Turing machines will have halting be undecidable. As was correctly pointed out, we write only a tiny fraction of Turing machines. But in practice, you may have noticed that in 50 years of doing this stuff, automatically finding bugs is still hard. Right? So in practice, we find that that it is hard, not necessarily undecidable. David Wagner did some very good work on this at Berkeley a few years ago. But still, in general, it's a crapshooter. We wouldn't be here. But then the question is, do we really need Turing machines for everything? We heard a talk about Kramer in the last session, which argued that no, we don't, in fact. You can, an awful lot of the Linux kernel can be done without that. So here, basically, but the question is, why do we use Turing-complete languages? Well, the answer is they're really easy. I mean, in fact, in some strict sense, we don't build Turing machines. Computers eventually run out of memory. There's a finite number of bits in the universe. So therefore, everything is finite state. But in practice, when we say Turing machines, it's because the state is so big that we might as well consider it to be infinite. And of course, they're powerful. I can do anything in language XYZ, right, for my favorite language. Well, yes, you can do anything in language XYZ, including shoot yourself in the foot, and my, what a nice hole you have down there. Because these languages are often much more powerful than is required to do the job, as the talk that we heard on Mocha just in the last session said. And they're impossible in general to verify. So why is that? Are there weaker models of computation where we can do rather better? The answer is yes. I mean, Turing-complete languages, verification is undecidable. Logic-free models of computation, by which I can also call these structural, these are in general polynomial. The most common example that we find is type checking in languages, right, which is essentially checking for structural consistency. So that's polynomial and for any reasonable type system, but it's also a relatively weak verification method. But in the middle, you have these things, state-free, which is to say it's logic, but the logic is purely a function of the input. There's no state at all in it. That, it turns out, is NP complete, but it's only NP complete. And the finite state runs the gamut between NP complete if you're using CTL, or all the way up to p-space complete if you're using LTL. It depends upon what variant of, that is computation tree logic versus linear temporal logic. So this is, the thing is that we tend to do this, and we tend to write programs in this. But this area in here, where the models are relatively powerful enough to do reasonable stuff, but they're still weak enough that you can actually have a hope of verifying these things, we don't use very often. And that's kind of too bad. So let's go to something of a cautionary tale. And this is why languages really matter. And this is Verilog and VHDL. Who's heard of Verilog and VHDL around here? All right. Has there anybody here who's written code in them? Is there anybody here who's liked it? You're a strange, sad person. Okay, I got my start doing this stuff. And it drove me absolutely mad. Because when the people who have written code in Verilog and VHDL know all about this. Hardware, the data path on a chip is state-free, right? It's an adder followed by a barrel shifter followed by whatever, right? You just plug stuff in. So that's combinatory logic. Control is a collection of finite state machines. And typically, by the way, you're not really interested in LTL properties when you go off and verify these things. So what that means is that actually we could no kidding do it, and can no kidding do it, right? There are many verification technologies. They use BDD-based data structures, powerful SAT tools. Kim McMillan won the ACM Doctoral Dissertation Award in the early 90s. There were a brace of great theses that came out of CMU in the early 90s about how to do this, all under Ed Clark, who eventually won the Turing Award for it. So this could, no kidding, be done. The problem was, it was hard to get designs described in the appropriate language. I mean, what Ken used to do, basically, is we go off, we take some Verilog code, or VHDL, we translate it into SMV, and then we go off and verify that. So, because by then, a design tool ecosystem had grown up around Verilog and VHDL, and as you can see, people much younger than I am still use this stuff, so it continues to this day. And the reason was just an accident of timing, because people started to do logic design using tools in the 80s, before logic synthesis and formal verification really took off, and their primary tool was a simulator. So Phil Morby built Verilog, and he just basically hacked it together. And it was so bad. It wasn't just the case that the semantics didn't match hardware. The semantics didn't match hardware. But forget that for a second. The semantics didn't match anything. Rick Riddell was working at Synopsys, and he was trying to build basically a Verilog compiler, synthesis system. And he used to call Morby and tell him what the semantics of Verilog were, because Morby didn't know. He just hacked it up. Then VHDL, which came out of the DARPA VISIC program, I'm told it was born from a losing aid effort. This thing actually did have semantics. Unfortunately, for both of them, the semantics didn't match hardware. Because what they had was a bunch of simulation control, right? How do I make the logic simulator work and go fast? Along with the hardware description. So as a result, it was really hard to tell what the hardware was. And you couldn't formally verify a design because you had to strip out all the simulation stuff that was gooed in with the hardware. And you couldn't even synthesize. And in fact, I remember I was on a panel at DAC, I think, in 1999 or something. And I was on hardware description language. And the guy from the VHDL users group said, VHDL is great. It's just that all the synthesizers suck. Yeah, great. That's because the language is an ambiguous piece of crap, right? I mean, gosh, C is great. You just can't write a compiler for it, right? This makes no sense at all. So finally, what we did was we put in synthesis semantics. In other words, figure out what was really hardware in all of this, and have a synthesizable subset of the language. And if you said, well, this is ridiculous, imagine a computational subset of C, Java, Python, and compilable subsets, you say that was nuts. And of course it is, right? So that didn't work out very well, and it's still limping along. There are still bugs in hardware designs. It's better, right? As with most things in the world, it's a mess. So fast forward about 10 or 11 years from that cautionary tale to this rather hopeful one. So how many people understand the guts of networking? A few people, all right? So what you know is that networking is a mess. But networking about 5 years ago became accidentally verifiable. And this was because, this was in fact entirely accidental. So it's a tale worth telling because it has some. So this is a traditional switch, basically. The data plane here is a stateless thing that just forwards packets according to some forwarding tables, which are basically a bunch of state-free stuff. More on that later. And the forwarding tables are generated by a controller that is sitting in a switch that actually the packets are coming through and going up. Some of them go up to the control plane to tell people the state of the network. But the controller is a Turingcomplete system, and and in fact what you have in the network is a bunch of them running a distributed algorithm to figure out how to send packets around. And of course, this is still unverifiable. You know, I mean, this is why you do Wireshark and stuff like that. So the network, you know, the good news and the reason people did this, network does control of data, is it runs completely autonomously, right? You don't need any external control at all. But the verification is, well, you have some CLI and SNMP and stuff like that, but it's basically runs on its own. So about 8 years ago, Nick McGeer and one of his graduate students at Stanford had this idea called software-defined networking. And the big idea here is off with its head. Let's rip the controller out of the switches. So now all the switches is a forwarding table and a data plane. I mean, this is idealized. It retrofits onto existing hardware, so nothing is so simple. But the basic idea is this is just a program running on some computer somewhere, where God intended programs should run, by the way. It's a very religious experience. And the data plane is simply forwarding packets, and the communication from the controller is just, here's your forwarding table, forward packets this way. Okay. So the network just forwards packets and sends state information to the controller, which generates the forwarding tables. So this does require an external controller, which is presumably a negative, but the verification on this is in MP. It's, in fact, MP complete because, well, this was done to make networks programmable, right? The original paper, Ethane in SIGCOMM 2007, was making networks controllable. But it also provided verification of something that a few people, like me, among others, realized, and suddenly verification started to appear. So suddenly you could prove that, hey, an OpenFlow network actually sent packets where it said it should, was loop-free, had various other properties that you cared about, right? And that was because the network of forwarding tables is isomorphic to a state-free logic circuit, right? AKA the data path of a chip, right? That's all it is. And so the verification methodology was that don't bother to verify the controller, right? But the controller is generating the state for the network coming out in these tables. So verify those. That we can do before you load it into the network, right? The controller could be a mess internally, but who cared? You could stop it from affecting the world by taking a look and saying, no, that wasn't, that set of forwarding tables isn't what we wanted at all. Better, you could actually do a safe update for the network, and I won't go into this, but this was actually a kind of a neat discovery, that you had, the network was in state 1, you wanted it to go into state 2, you had to send out updates to the switches in such a way that you didn't bust any invariant, and you could actually derive a schedule that would do that, or you could prove that there was no such schedule, that there was no safe path from one to the other. And so, and moreover, even better, the network specifications were often state-free. So, because when the idea was, gee, let application writers specify the network that they want, much as a storage application designer gets to say, here's how I want you to lay out blocks on disk, which you can. But it turned out that when people did that, what they actually said was, here's a graph of the network I want, here are the weights on the edges, controller, make it happen. Well, this desired network specification is state-free as well. So this is finite or state-free, and therefore verifiable. The output of the controller is, so the inputs to the controller are verifiable, right? This is the network I want. The outputs are verifiable. Yeah, it doesn't have any bad properties and it's what you wanted. And so even though this thing was a total mess, or it could be a total mess, in fact, it is a total mess if you look at open daylight, the system as a whole is completely verifiable. So by controlling this undecidable stuff in the middle, or hiding it and just looking around the edges, you could actually come up with a verifiable system with a key unverifiable component. Okay, we're moving beyond SDN to SDI. And I've been going for, I've been going, 10 seconds. It doesn't tell me much. All right, I've been going from SDN, and what software-defined infrastructure is you go beyond defining the network, but defining the whole ecosystem. Allocating containers, populating them with software, kicking them off to run various things, controlling the network between them, go Amazon, Genie, whatever, and make it happen, right? So the key problem is configuring the underlying infrastructure to do your application. And what you'll typically do is allocate VMs and containers using something like Nova. Use software-defined networking to configure the networks, maybe working through a tool like Neutron, or better yet, ONOS, if and when that ever gets, well, that is going to get released. And then use and writing your configuration code in something like Frenetic, which is state-free, and then use an orchestration engine, something like Ansible and Heap. And if you take a look at how these things work, these are either finite state, in other words, or state-free markdown, or restricted state, which is to say you can load stuff into variables, but that isn't used in logic, and they don't have things like loops and stuff like that. So it can hold values, but these things actually look like wires. So what that means is that, hey, look, we can verify what is. We can say your application deploys properly, the network is configured properly. You know, maybe your application still stinks. That's always a possibility, but at least we can prove we did the right thing of putting it out. So that's a nice thing, number one, which is, and that's actually the next thing I'm going to be doing in a new operating system that we're building to control cities. But that leads, but this is the next to last slide, which I'm sure everybody's going to be happy about, which is that this leads me to a wild speculation. Is verifying Turing machines really undecidable? And the answer is, well, of course, you know, there are theorems about this. But the theorems don't say, you know, you can't tell if the system's going to do what it wants. It says you can't tell if this Turing machine is going to do something reasonable. So if we take a look at this diagram of software-defined networking that had a Turing machine sitting at its heart. So the whole thing, you know, that thing, that was undecidable. But the system as a whole was decidable because it was surrounded with enough finite verifiable stuff that whatever garbage it was doing in the middle didn't matter because we could verify the inputs to the Turing machine's outputs. So we can do the same thing with these little with these deployment engines that set up an infrastructure for people. But could we do the same thing with German programs? Can we surround a program or components of a program with verifiable models and verify this stuff in situ? And this, as I say, utterly wild speculation. So back when we were doing hardware for a living, when I was doing hardware for a living, basically the stuff you were verifying looked like that. It had some finite state input generator, right? So the world behaved like a finite state machine, and it pooped stuff out at your hardware design, which was another finite state machine. Might be big and complicated, but it was a finite state machine. And it too would interact, and then you would have some output specification, which is, here's what I think the output of this thing should look like. And you'd take the tensor product of these guys, and you go and you say, can this thing ever get into a wedged state, right? Where you have some specification of what wedged would look like, so you were able to verify it. so that we could verify. Now, what we have here in general in the world is we have some arbitrary uncharacterized inputs, a Turing-complete program that we can't verify, and some outputs, and then we want to say, do the outputs do the right thing to the inputs? And of course or does the program do the right thing to the inputs to produce the output? Well, we don't know that. But what we do know, and there are finite state modeling tools that will let you take this for a program. The trouble is that you can't prove that the program itself, when it runs, corresponds to your finite state model, right? Or that the inputs are behaving as the finite state generator says. But in fact, when you're actually running the program, you can bisimulate, right? You can run the finite state input thing, and in real time against the program, and constantly check: does this thing actually correspond to what the output has done? And already, actually, programmers do this with assert statements. Right, what these things are is it's basically runtime model checking within the body of the program. The problem is that the model checking is mixed with the execution code, so it's hard to disentangle and disambiguate. And I've been through that once, and it's bad. It complicates the execution. It makes the model hard to extract, right? You have to look at this collection of assert statements and say, well, this is really what this guy is trying to say as a model. And it also makes the execution code more complex than it has to be, because you can't disentangle what's actually doing something as opposed to what's checking itself. And also, it's not coupled to any formal verification engine, so you can't construct proofs. So I think actually doing something like this is a significant research opportunity. So that's the final word. We need to design. Basically, I think the computational environments and languages need to be designed with an eye to verification. But it doesn't mean that you need to actually go off and redesign the guts of the language. I've been through that one before too, and that's really hard because ecosystems grow up around these things. There's tools, there are programmers, there's compilers, and there's culture. And these things are all very, very hard to change. But what you can do is surround these things with models and construct bridges between the models and the programs themselves and get some verification. The attraction to a developer on this, by the way, is, you don't have to put some assert, you don't have to put so many assert statements in, does the input look weird, all that stuff in your code, because the model, if it's wrapped around properly, takes care of that. But the key is clean separability and use the runtime information to validate the correspondence. And with that, thank you very much for your time.